Welcome back to our series on robotic path planning and OpenPilot. In today's episode, we'll delve into the fascinating world of car control and information storage in the context of OpenPilot. We'll explore the car controller params, car controller, car state, and car classes, examining their roles and functionalities within the system. So let's dive right in. 1. Car controller params. To begin, we'll explore the car controller params class. This class plays a crucial role in defining various limits and allowances for steering and acceleration control within the OpenPilot system. It enables effective and safe control of the car's actuators based on the provided parameters. In the code snippets provided, we encounter multiple instances of the car controller params class, each tailored to different car models or manufacturers. Let's take a closer look at each instance and its significance. The first instance represents the lead Kalman filter parameters for a radar-based system. It includes a lookup table to compute optimal control values for different time steps. This instance plays a vital role in calculating the gain matrix K for the Kalman filter, contributing to accurate and reliable radar-based control. Moving on, the subsequent instances of car controller params define parameters for steering control in specific car models. These parameters encompass steering step, torque limits, and driver allowances. The values of these parameters may vary based on the specific car's fingerprint or transmission type. By customizing the parameters according to each car's characteristics, OpenPilot ensures precise and responsive steering control. Furthermore, we encounter additional instances of car controller params that set parameters for steering control in different car models. Each instance defines the steering step, torque limits, and other control constants specific to the respective car's fingerprint. By tailoring the parameters to individual car models, OpenPilot optimizes the control system's performance and adaptability across various vehicles. Lastly, we come across an instance of car controller params that sets parameters for both steering and acceleration control in a car. This instance includes values for steering step, torque limits, and other control constants specific to the car's fingerprint, such as RAM HD or RAM DT. By accounting for the car's unique characteristics, OpenPilot ensures seamless integration and efficient control across diverse vehicle models. 2. Car controller. Now that we've explored the car controller params class, let's shift our focus to the car controller class. This class serves as a crucial component in the OpenPilot system, responsible for controlling the car's actuators, including steering, gas, and brakes. In the code snippets provided, we encounter different implementations of the car controller class for various car models. These implementations showcase the control logic and algorithms utilized by OpenPilot to steer and maneuver the car effectively. In the first code snippet, we find a generic car controller implementation. This implementation initializes the controller with various parameters and PID controllers for speed, balance, and turn control. The update method calculates the desired speed and angle based on joystick input and feedback from the car's sensors. It then updates the torque values for the left and right wheels and sends control messages to the car's CAN bus. By employing PID controllers and intelligent control algorithms, OpenPilot ensures smooth and precise control over the car's movements. Moving on to the second code snippet, we encounter a car controller implementation tailored to a specific car model with additional functionality for hands-on detection and steering control. This implementation updates the steering angle based on the joystick input and the car's current state. It also handles longitudinal control to maintain the target speed and cancels the cruise control on user override. By incorporating hands-on detection and advanced control logic, OpenPilot enhances the safety and responsiveness of the car's steering control. Continuing our exploration, the third code snippet presents another car controller implementation designed for a different car model. This implementation applies torque limits based on driver input and updates the steering angle accordingly. It also handles alerts and cancels the cruise control on user override. By integrating torque limits and sophisticated control mechanisms, OpenPilot optimizes the control system's performance and ensures safe operation in diverse driving scenarios. In the fourth code snippet, we encounter yet another car controller implementation for a specific car model. This implementation updates the steering angle based on the joystick input and the car's current state. It also handles cancelling the cruise control and sends messages for HUD alerts. By considering the car's unique characteristics and leveraging advanced control algorithms, OpenPilot enables accurate and responsive steering control tailored to specific car models. Lastly, the fifth code snippet presents another car controller implementation for a specific car model. This implementation updates the steering angle based on the joystick input and the car's current state. It also handles cancelling the cruise control and sends messages for HUD alerts specific to this car model. By incorporating model-specific control logic and feedback mechanisms, OpenPilot ensures optimal steering control and a seamless user experience. 3. Car state. Now that we've explored the car controller class, let's move on to another crucial component of the OpenPilot system, the car state class. This class is responsible for storing and updating the state of a car, providing real-time information about its various attributes. In the code snippets provided, we encounter multiple implementations and variations of the car state class, each contributing to the accurate representation and tracking of the car's state. Let's delve into the details of these implementations. In the first code snippet, we find an update method within the car state class that processes the PT_CP control packet. This control packet contains essential information about the car's state, including wheel speeds, speed, gear shifter position, brake status, gas pedal position, and steering angle. The update method extracts this information and computes derived attributes such as standstill status, brake pressed status, and gas pressed status based on the extracted values. By accurately updating the car's state attributes, the car state class provides a comprehensive representation of the car's current condition. To facilitate the parsing and processing of control packets, the car state class also includes the get_can_parser method. This method returns a can_parser object specifically designed for extracting the desired signals from the control packets. The can_parser object specifies which signals to parse and their respective check frequencies. By utilizing the can_parser object, the car state class ensures efficient and accurate extraction of the required information, further enhancing the fidelity of the car's state representation. In the second code snippet, we encounter an alternate update method within the car state class. This update method incorporates three types of control packets: PT_CP, cam_CP, and loopback_CP. By including information from these packets, the car state class can enhance the accuracy and completeness of the car state updates. Similar to the previous update method, this version extracts relevant information and computes derived attributes to reflect the most up-to-date state of the car. By incorporating additional control packets, OpenPilot obtains a more comprehensive and detailed understanding of the car's state. Additionally, the car state class provides the get_cam_can_parser and get_loopback_can_parser methods. These methods return can_parser objects specifically designed for parsing camera and loopback control packets, respectively. By using different can_parsers for different control packet types, the car state class ensures efficient and accurate extraction and processing of the required information. This sophisticated parsing mechanism enables OpenPilot to stay up to date with the car's state, enhancing its ability to make informed decisions and execute precise maneuvers. 4. Car. In our final segment, we'll explore the car class within the OpenPilot system. This class, along with its subclasses, plays a vital role in storing and retrieving information about different car models and their compatibility with OpenPilot. The code snippets provided introduce three classes: GM Car Info, VW Car Info, and Car Info, each contributing to the comprehensive storage and retrieval of car information. The GM Car Info class, a subclass of Car Info, represents GM cars within the OpenPilot system. It specifies the required package for adaptive cruise control, ACC, and defines the necessary car parts for GM vehicles. Additionally, the initialization method of the GM-CarInfo class checks the network location of the car to determine the appropriate car parts to be used. By accurately capturing GM car-specific information, the GM-CarInfo class enables effective integration and compatibility with OpenPilot. Similarly, the VW-CarInfo class, another subclass of CarInfo, represents VW cars within the OpenPilot system. It specifies the required package for ACC and lane assist, as well as defines the car parts necessary for VW vehicles. The initialization method of the VW-CarInfo class adds footnotes and checks the car fingerprint to determine any additional car parts required for specific VW models. This attention to detail ensures seamless integration and compatibility between OpenPilot and VW cars. Now let's delve into the base class, CarInfo. This class serves as the foundation for car information storage within OpenPilot. It defines common attributes and methods used for all car models, facilitating efficient and structured information retrieval. The CarInfo class stores essential information such as car name, required package, video links, footnotes, and car parts. The init method initializes the car information based on the car parameters passed to it. It determines the availability of OpenPilot, sets minimum steer and enable speeds, checks hardware compatibility, and assigns values to various columns such as make, model, package, and more. Additionally, it calculates the steering torque star based on the car's maximum lateral acceleration. The CarInfo class also includes a get_detail_sentence method, which generates a sentence describing the car's OpenPilot capabilities, and a get_column method for retrieving specific column values in the appropriate format. By utilizing the GM-CarInfo, VW-CarInfo, and CarInfo classes, OpenPilot effectively stores and retrieves information about car models and their compatibility. This information is crucial for robotic path planning and decision-making, as it allows the system to understand the capabilities and requirements of different car models, enabling effective navigation and informed choices.